Well, good morning or whatever time it is where you are. Welcome in abstention to Humke's study. I'll be back on Friday, but let's take a look at a couple applications. The applications that we're going to be dealing with in here, at least for a while, this first band of applications, all involve integrating a function over a region. And for the region will be a variable. It can be almost any region. The function, on the other hand, will be chosen to give you some information. So the application that we're talking about all involve matching a function with what you're going to integrate and how you're going to use that function. So the first application is the average value. And you're going to find the average value of a real valued function. All of our functions here will be real valued. So, and there are two integrals involved. The integral of the function itself that is given, like temperature, for example. And the second one is the area of R, which is given by this integral. The integral of 1 always gives you the measure of what you're integrating over. So this is the average value. So if I say average value, this is what to compute. Now, there are other things that we'd like to look at. Total, I'll use mass, kilograms, but this could be charge, electrical charge, and many other things. What you'll be given to do this is a density function. I thought I'd just talk a little bit about what the density function is. If you have some solid object, so this should be looking like a three-dimensional object, but if you have a solid object and you take a point in it, here is how the density function is defined. Density is more or less mass at a point. Or another way mathematically to look at it, it is the derivative. It is a derivative of mass, and this derivative is kind of a three-dimensional derivative, and let me show you what that means. So we take a point in the object, and we take a small, let's say, epsilon cube about this, epsilon by epsilon by epsilon cube, centered at that point. Now, this cube has mass. So you look at the mass of the cube, whose radius is, or whose side length is epsilon, and divide by the volume of the cube. And so this gives the mass as a function of epsilon divided by epsilon cubed, the volume of the cube. And then you take the limit of this as epsilon goes to 0. Math is always taking it to the limit. And this is called a density function. This gives you a density at this point, xy. So taking this to the limit gives you this density function xy. So this is the definition of density. It is a type of derivative. This is what you will be given. If, sort of a special case, when the density is constant, or 1, If the density is constant, then these things are considered to be geometric. If the density is 1, then the integral you get of the density function over R is the integral of the 1 function, which is the measure of R, in this case, the area of R. Or if R was 3-dimensional, this would give you the volume of R. So the special case is this case where the density is constant or 1, where this is just giving you geometric information about R. If the density is different from 1, depends on x and y, maybe x squared plus y squared, then this is giving you something about the mass distribution. Okay, so the total mass of R is then the integral over R of the density function. And since this is a double integral and plates sort of don't have mass since they're infinitely thin, we're going to be thinking about a plate that has equal thickness and all of these cross sections from top to bottom interior here. The density is constant on those little stubs. And so what we'll be getting here is not the mass of an infinitely thin plate, but the mass of, this is called a lamina. So this is what this integral is going to give us. Now I'm going to erase this and go to the next one, next application, which will use this one. And the application I want to talk about is find the balance point of a lamina. So for example, if we take a disk in the plane and it has a little thickness, and now we have a density function. If the density function is constant, then the balance point of this is just the center, 0, 0. And you can think of finding that balance point in the following way. I need a lamina here. My lamina is missing. So I'm going to have to do with a small lamina. So if we take this small lamina, one way to find the point at which it balances, so we want to balance this on a needle, is to balance it in 2 linearly independent directions. In our case, it'll be x and y. So we balance it this way, and then we balance it this way. And where those 2 balanced edges intersect is the balance point, or the center. If rho is 1, then we're going to find the geometric center. If rho is not 1, then the center will not be at the origin, but might be here, meaning there is more mass on this side than there is on this side. It looks like the mass is evenly distributed along this line, but we are after this balance point. And the way this works is exactly the way a teeter-totter works. You compute 2 first moments, the moment in the x direction and the moment in the x direction is the integral of x over the region. And if there's a density function, it's x times that density function. The moment in the y direction is the integral over r of y times rho of x and y. if you didn't do these, if you didn't see how this works as a balance point in Calc 1, there's plenty of stuff on YouTube for showing you why the teeter-totter, how to find the teeter-totter balance point, and that's what we're doing here exactly. So these are the two integrals that give you the moment, and then the center, the balance point, consists of the moment in the x direction divided by the mass, and the moment in the y direction divided by the mass. So each of the x and y's is sort of like an average value, but you're not averaging the function itself. You're averaging the function times x and the function times y, because what you're interested is not the average value, but the balance point. And that is weighted by how far these points are away from the balance point, in this case in the x direction, and in this case in the y direction. So let's take a look at an example of this. Let's find the balance point of the disk x squared plus y squared less than or equal to 1, and y is bigger than or equal to 0. So we want to find the balance point of that. And so we're looking at this region, and let's just find the geometric center here. So I'll set rho equal to 1. And so some things are obvious from the nature of what we're finding. The moment in the x direction should be 0, because this is balanced along over the y-axis. So the y-axis is going to balance this lamina if we're looking at it vertically. The area we can find is pi over 2. So we can find the quote mass in this case is just going to be pi over 2. So the thing we have to find is the moment in the y direction. Where is the balance point in the y direction? But let's take a look. Maybe we'll compute both. So the moment in the y direction is equal to the integral over this semicircle, SC, and it's just of the y value. So now this amounts to being able to describe the semicircle in a reasonable way. We can use Cartesian coordinates, but this is sort of set up for polar coordinates. So I'd like to do a polar integral. If you do a polar integral, r will be between 0 and 1, and theta will be between 0 and pi. That describes the region polarly. So this is equal to the integral. R will go between 0 and 1. Theta 0 to 2 pi. We'll have y. We'll have an r dr d theta. The r is the expansion contraction factor due to the change of variables, the polar change of variables. We already computed this, the determinant of the derivative. Okay, so I'm going to erase my picture. Let's compute, see what we get. So we are polar coordinates, so y is equal to r sine theta. So we have the integral 0 to pi, integral 0 to 1 of r sine theta times r again, dr d theta. All right, sine theta, we can do this by hand. So this is integral 0 to 1, integral 0 to pi. R squared comes outside the first integral. No, sine theta comes outside the first integral. Sine theta, the integral of r squared from 0 to 1, dr d theta, equals. So this integral is just a third, r cubed over 3 between 0 and 1. And the integral of 0 to pi, sine theta d theta. Integral of sine is minus the cosine theta over 3 between 0 and pi. Pi, the cosine is minus 1. So this is minus a minus 1, or 1/3. Minus the cosine of 0. So minus, it'll be minus this. So it'll be plus another 1. So this is 2/3. I did that right. So the moment in the y direction is 2/3. So let me erase my work here. And just record this. The moment in the x direction is 0. You can do that integral if you want. The x is just r cosine theta. And if you integrate, you do get 0. The mass of this thing is equal to, in this case, because we took rho equal 1, the area, pi over 2, center, moment in the x direction over the measure, so we get 0. Moment in the y direction over the measure, 4 over 3 pi. And we might check out to see if this makes sense. 4 over 3 pi is a little less, if you went up half. So this is a little less than half. Would be the balance point. Yeah, could be. So geometric centers, centers of mass, mass itself, or total charge, something like that, all integrals of these moments are integrals of x and y times the density. Now, just a little bit more. If we take an object like this, we can also find that center by taking the moments about other lines. So any two linearly independent directions, say these two directions, we could integrate, take a point of the region. And if we're talking about the green line, we could integrate the distance to the green line. We should measure the green line in the blue direction. So we could integrate this distance, and then we could integrate the distance to the blue line in the green direction. And similarly, find two different moments. These are linearly independent directions. So using the same information, it will tell you how to find the center. So any two linearly independent directions work, but in general, you use the x and y axis. It fits well. Sometimes, though, it can be convenient to use other lines. The other thing I thought I'd show you is the second moments. These are important in lots of places, but they're important in physics, but they're also very important in statistics. In particular, when you're looking at things like the central limit theorem of statistics, which sort of has a central place in the discipline. these second moments are important. And again, there's a second moment in the x direction and a second moment in the y direction. And this will be the integral. Again, we'll have a density function involved. And here, if it's in the x direction, we multiply by x squared over the region. And in the y direction, you are looking at the integral over the region of y squared, rho of x and y. So these are called second moments or moments of inertia. And these moments of inertia tell you how stable this object is if it's rotating. It's a rotational, it gives you a rotational equivalent of first moment. And these are used for a number of things. They're used in engineering to study stability of various objects that are undergoing torque. And they're also used in physics. There's also a polar one, I sub p, which is the sum of these two. And when you sum these two, you'll see that you're integrating x squared plus y squared against the density. And so I'll give you a few problems that involve moments of inertia as well as special single moments. So first moments, moments over mass, give you centers, they give you balance points. Second moments, moments of inertia, give you another measure of the physical quality of your lamina. Density is a density function. You integrate it to get the total mass or total charge, depending on what it's the density of. And that's about it. So I'd like you to know these particular applications, give you some problems about them, and see you Friday.